we introduce a training-free open vocabulary semantic segmentation method, distilling spectral graph for object context-aware open vocabulary semantic segmentation. Open vocabulary semantic segmentation, or OVSS, aims to segment unseen classes based on user-provided prompts. For example, when given an input image and a prompt like Space Needle, the model should accurately segment both general objects and specific proper nouns. Training-free approaches are particularly advantageous for OVSS. Unlike fully supervised methods, which often overfit to seen classes during training, training-free methods leverage large-scale pre-trained models to achieve better generalization. They also enable direct application to real-world scenarios without the need for additional datasets or retraining. This makes training-free methods highly aligned with OVSS's goals. To achieve the true goal of OVSS, many studies have explored training-free approaches to better align with its objectives. However, they face limitations in capturing object-level context. To grasp object-level context, please refer to this illustration. Components comprising a truck, such as its wheels and cargo area, should be grouped as a single entity. Similarly, components of a sheep should be accurately unified under the correct user-given object class. To address this, we propose CAS, which incorporates object-level context into training-free OVSS. First, let's briefly review the baseline pipeline. We use CLIP for image-text alignment and modify its visual encoder for dense prediction. Specifically, we adjust the self-attention mechanism in the final layer. Instead of using the standard attention map computed as the dot product of queries and keys, we compute the dot product between keys to produce a CLIP. This modified attention map is projected into SLIP's latent space, and patch text similarity scores are computed using text embeddings. Now let me explain our proposed method. Although we modified the CLIP attention map, it still lacks object-level context. To address this, we propose spectral object-level context distillation. This method enhances intra-object consistency by transforming VFM's patch-level attention graph into object-level representations and distilling these into CLIP's attention map. However, a question remains. How do we account for the multi-head attention mechanisms in both VFM and CLIP? Recent studies have shown that different attention heads focus on distinct parts of an image. To account for this, we propose matching attention graphs with contrasting structures, enabling VFM to supplement the object-level context that CLIP struggles to capture. After computing the attention graphs, we analyze their structural features by performing eigenvalue decomposition for each attention head, allowing us to effectively compare and match their unique characteristics. To quantify structural differences, we construct a cost matrix by comparing the spectral distributions of eigenvalues using the Wasserstein distance. This cost matrix is used in the Hungarian matching algorithm to pair attention heads between VFM and CLIP, facilitating complementary knowledge exchange. As shown in the figure, this process matches structurally distinct attention graphs from VFM and CLIP. For clarity, I will focus on explaining the matching results of these two graphs. Since VFM represents patch-level information, it needs to be transformed to emphasize object-level representation. To achieve this, we perform energy-based low-rank approximation to preserve essential object-level contextual features while discarding noise and irrelevant details. Additionally, we propose dynamic eigenscaling, further emphasizing critical structural information, particularly object-level context features. This facilitates the transformation of VFM's patch-wise representation into object-level representation. After transforming the VFM graph into object-level context, it is distilled into CLIP. During aggregation, spectral distance adaptively assigns higher weights to graphs with complementary structures, while minimizing the influence of similar ones. The figure highlights the effectiveness of our method. The middle column shows the results of aggregating CLIP and VFM without transformation, failing to capture the entire object. In contrast, the right column demonstrates our approach, achieving strong intra-object coherence. The spectral object-level context distillation enables precise object mask generation. However, due to the nature of OVSS, where users provide arbitrary query prompts, parts of the same object may still be assigned to closely related categories. To address this, we leverage CLIP's strength in zero-shot object classification by utilizing its object presence prior and propose two methods to incorporate it. First, we use the object presence prior to adjust text embeddings, ensuring they reflect object-specific semantics. To avoid assigning similar prompts to different components, we group semantically related prompts by measuring their distances in the CLIP embedding space and clustering them hierarchically. We then compute the object presence prior by projecting the CLIP class token into the visual embedding space and computing its dot product with text embeddings, extracting class-wise probabilities. Based on this prior, we select text embeddings from the grouped prompts that are most likely to correspond to objects in the image. Next, we refine the selected text embeddings to better capture object-specific semantics. Patch-wise visual features aligned in CLIP's latent space contain object-specific semantic vectors that can guide the text embeddings. We adjust each selected text embedding towards the average vector of the most semantically similar object-specific vectors, ensuring the embeddings accurately represent object semantics. Finally, we integrate the object presence prior with patch text similarity to generate an object-centric segmentation map. This approach combines class probabilities from patch text similarity with the prior, improving predictions for objects present in the image and enabling better object grouping. We evaluate our method, CAS, on 8 datasets with the number of classes detailed in the table below. The table summarizes the main quantitative results using CLIP base 16 and Dino base 8, evaluated with the MIOU metric. Models marked as fair share the same evaluation settings as ours. Our method outperforms existing training-free approaches, showcasing its effectiveness. Notably, CAS also surpasses models requiring additional training, further demonstrating its robustness. The figure qualitatively compares our model with recent state-of-the-art training-free OVSS methods. By emphasizing object-level context, our model ensures better grouping of individual objects. As shown by the white circles, it excels at grouping slender components, such as animal legs or human arms, effectively capturing fine details. Thank you for listening.